Hello, I'm Vasileios Trigonakis, and together with my colleagues in Oracle Labs, we have developed aDFS, that is a fast and scalable distributed graph query system. Now, most of you know that graphs are a very important workload nowadays, and graph processing is one of the most powerful tools in the toolkit of any data analyst. In the Oracle Labs PGX project, we have been developing a complete graph solution that includes PGXD, that is a distributed graph engine for very large graphs. Now, regarding workloads, graph queries are one of the most commonly used and the most expressive ways of analyzing graphs. So graph queries allow the flexible exploration and analysis of graphs, and they're essentially very similar to what SQL provides for relational databases. In our solution in PGXD aDFS, we use PGQL, that is a graph query language that is modeled after SQL. So let's take a look at a simple example where we are asking for information of two authors who like each other. So as you see in the query, we have a select, the where, and the order by clauses, exactly as you would have them in SQL. But we also have the match clause that allows the user to define patterns to be matched against the data graph. And in this example, we have an author A1 who likes an author A2, and author A2 also likes A1. Now, in terms of semantics, this matching requires homomorphic matching of the query pattern to the data graph, and it also returns all result permutations, so there is no result pruning, because we are projecting and filtering data in the graph, which means that every vertex, every edge is an independent entity. Additionally, as you see in this query, the user can write any expression for filters and projections, which shows the expressivity of the language. Now, these need to support any user expression, and they require for homomorphic matching with all result permutations, are part of the reason why it is complex to support efficient graph query execution in any system. Of course, apart from these two, in graphs, typically you have limited locality because of the following edges or following pointers. So we do edge chasing, and this limited locality becomes an even more important problem in a distributed system where by design, some of your edges will bring you to a remote machine, so no locality. Another complexity in graph processing that is generic to graph analytics is the intermediate and final result explosion as you're matching things on the graph. So on this slide, I have put a simple example on the Twitter graph where in the first query, we're matching the complete graph, so a one-hop relationship. So there we get 1.4 billion results, that is the number of edges in the graph. And then in the second query, we're matching like two hops, so A, B, C, let's say. And as you can see here, we immediately get like a result explosion. So this query gives you 9.3 trillion matches. That is, of course, a massive exploration space. So what we claim is that you need a distributed query engine to support the massive scale of some of graph queries, but also a flexible solution that allows you to support the expressivity of graph queries. And this is exactly what we have gotten with PGXD aDFS. So small spoiler, with PGXD aDFS, we can support with 8 machines this query in less than 20 minutes and to return these 9.3 trillion matches, which translates into something like 8 billion matches per second. So in the rest of this presentation, I will give you an overview of how aDFS achieves this good performance and good scalability and ability to process very large graphs. I'll show you some very brief evaluation results of aDFS, and then I will, of course, conclude the presentation. So let's take a look at the principles behind aDFS. So aDFS first relies on asynchronous operation whenever possible. So workers in aDFS operate on different parts of the query, so on different traversals of the query, and essentially they are focused on where there is enough work. But the thing is that workers can operate on different parts of the query independently. And then when a worker in aDFS needs some remote data, it simply buffers the intermediate result in a message targeting the remote machine, and then it continues with some other local work. So all in all, there is like workers in aDFS do not block due to remote communication. And the second principle behind aDFS is the depth-first execution of queries. So aDFS always tries to prioritize later parts of the query in order to take intermediate results and eagerly make them final results, or essentially reducing the memory that is used for the query execution. This, combined with a fine-grained flow control mechanism, allows aDFS to control and cap the maximum memory consumption during pattern matching. Let's take a look at an example why this limiting the memory consumption is very important. So we are comparing aDFS with a BFS engine, where every part of the query, every hop of the query is fully materialized. So, and we do this on a very tiny graph of 5 million edges. And here, like we use a workload of like accounting like different lengths of cycles. So on the x-axis, we have the memory consumption per machine. We use 8 machines here. So we see that for 4 hop cycles, both engines, both algorithms perform more or less the same. But then as we go on to 5 hops, you see that the BFS algorithm already consumes a lot of memory. And for 6 hop cycles, even on this tiny graph, BFS cannot complete the query because it consumes more than the 6 terabyte memory of cumulative memory that we have in the system. So we see that there is really a need to control the memory consumption in a graph query system. So all in all, what aDFS offers is a fast in-memory distributed execution of queries with controllable max, like a capped memory usage. So let's deep dive a bit more on how does aDFS achieve this. So as we said earlier, a user gives aDFS a PGQL query. And this, of course, needs to be translated into an execution plan that aDFS knows how to execute. To do this, the query goes through 3 transformations. So first it becomes a query plan, then a distributed query plan, and then we get the execution plan. I don't have the time to go into the details of these transformations, but you can find, of course, everything in our paper. Now, what I'll show you here is how does an execution plan look like. So an execution plan in aDFS is a list of stages where every stage knows how to match a vertex and how to move to the next stage, if any, or produce a final result if we are talking about the last stage. So here in the example, we have 4 stages, 1 for each of A, B, and C and D vertices that we are matching in the query. So let's use now this like a stage-based approach to explain how aDFS implements asynchronous DFS BFS traversals. So we have here a graph that is partitioned across 2 machines, and we'll see an activity diagram and an example from the point of view of an aDFS worker who is matching the query to this data graph. So we have already matched stage 0, we have matched A here, and the worker needs to follow the next edge in order to go from stage 0 to stage 1 and so forth, right? So if we are talking about local edges, aDFS supports depth-first execution, meaning that it can go from stage 0 all the way down to the last stage for this single intermediate result and produce the output, as we see in the example here. However, for remote edges, the policy is different. So for remote edges, the worker simply buffers the intermediate result that is targeting machine 1 in a message, and it can then continue with some other local work as long as this buffer is not full. When this buffer, message buffer becomes full, then aDFS tries to send this message, and this might be allowed or not by the flow control mechanism that keeps track of the memory consumption of this query. If the flow control detects that it is okay to send the message, then the worker will simply send the message and continue with other work. Otherwise, flow control might not allow the sending because it would violate the memory requirements of the query, in which case the worker puts this message buffer on the side and it performs other local work like receiving a message and processing this received message. Later, of course, the worker thread retries to send this like a blocked message. And of course, it needs again to request for like a flow control approval. Now, on the receiving side, when a message is received, it is eventually picked up by a worker, and it is, of course, expanded based on the same approach that we discussed here until this becomes like a final result, or some intermediate results are dropped because of the filters or of not having any edges to follow. Now, here I showed that like for local edges, like aDFS follows a strict DFS approach, but we observed that this might not be the best idea because it might lead to some threads doing some very heavy local DFS work, while other workers might not have enough work to do. So we detect these conditions automatically in aDFS, and we switch to per thread buffered BFS locally and work sharing to alleviate this problem. Unfortunately, I don't have the time to go into the details of this or the other parts of the aDFS runtime in this presentation, but you can find all details in our paper. So let me move on and show you some like basic experimental results comparing aDFS to other systems. So on this experiment, we are comparing aDFS to Apache Spark GraphFrames, to Neo4J Community Edition, MongoDB, and Postgres on 4 different graphs. So the 3 are very well-known graphs in the community, LiveJournal, Twitter, and WebGraph, respectively. And we also have included a random 1 billion edge graph. And the queries that we execute on these graphs are 2 very simple count queries, where we are counting in query 1 cycles, so ABA, and in query 2 like a simple 2 hops path, so ABC. Now on the y-axis we have the latency in seconds in log scale. So for LiveJournal, as you can see, all engines are successfully able to complete the query, but of course you can already see that the aDFS is significantly faster than the others. Now, as we increase the size of the graph and go to the random 1 billion graph, you see already that some engines struggle to complete the query in a reasonable time manner. And then if we move to the largest 2 graphs, we see that like most of the engines cannot really process this computation. So in particular, if we look at the largest 9.3 trillion query 2 on Twitter, that I mentioned also earlier in my presentation, you see that only aDFS is able to complete this query. So all in all, we claim that only aDFS can really handle this extreme scale that some graph queries may require. So I will not have the time to show you more experiments, but of course in the paper we have a detailed analysis of the performance of aDFS. We use also LDBC to compare aDFS against the engines that we have here. And we also have a very detailed and thorough comparison of aDFS with various state-of-the-art graph mining systems. So with this, I will complete this presentation. So I introduced aDFS, that is a fast and scalable distributed graph querying engine that provides a flexible PGQL API. And it combines BFS, DFS, and like a flow control mechanism to allow fast performance while limiting the maximum memory consumption of the system. So in our current and future work, we are looking at extending aDFS with more PGQL functionalities like reachability path queries, subqueries, shortest and cheapest paths. So with this, I want to thank you for your attention, and please do not hesitate to reach out to my email for questions, but also for internship and job opportunities in Oracle Labs. Thank you.